So today we're going to be talking about a topic called cryptography. Now, I'll be providing a brief introduction to this topic, which is quite a broad topic, just to be very clear. So I want to give a little summary about what cryptography is, and then we're going to talk about some core terminology in relation to the things that we're going to be studying here. So let's do that here. So let's first talk about what is cryptography. So cryptography is the study, I was about to get right to the chase. It's the study of, oh, here comes that M word, mayonnaise. Okay. The mathematical techniques related. And I must stress that this is just a brief description. I must stress that we can go into all sorts of niches into this topic. Techniques related to information security. For instance, that's one way you could think about it. Security. Such as, and there's different aspects to this, such as confidentiality. This is one that we'll mostly focus on. Confidentiality. Data integrity. For those that aren't sure what I mean by this, what I'm saying is, I haven't forgotten, Miss Katie, don't worry. Ensuring that no one is allowed to change the data. So if you have data and you want to make sure that it doesn't get compromised, that's what I'm referring to. There's different aspects to such things. So we can talk about protocols that are put in place to ensure no data has been changed. This might also include authentication, which is another big aspect of cryptography. Authentication. So authentication in the sense of data, this could just be simply the idea that of who you're talking to, authenticating that. So, namely, we will be interested in the study of techniques for so-called secure communication, for secure communication. So this will include things like protocols and more over an insecure communication channel, which I'll talk more about that in a moment. You can't just throw a term like this out there and be like, okay, whatever, just go along with it. No, I'll go into more detail about what I mean by communication channel and what it means to be insecure. Where an agent may be interested in what we are communicating. So perhaps that might include more things, whether it be malicious or not. But we'll be focusing in on the study of techniques for secure communication over an insecure communication channel, which is a standard model for cryptography. So let's go through some basic terminology. Miss Kitty's going to help me talk about this. So let's do some basic terminology. So the first thing I'm going to talk about is something called a plaintext. So you're going to imagine you have this communication that's happening over this channel where I have some message I would like to send over the channel to someone else. So the message in question I refer to as the plaintext. The message M, or data to be encoded or sent. So often I'll use lowercase letters to indicate that I'm referring to plaintext versus another. So when I send it over this channel, I would like to be able to do something to protect it from other people interested in what I'm sending. I would like to have some form of security. So we'll talk about that in a moment, but whenever I have the message in question, M, I'm always going to write it with lowercase letters, but this is just me trying to be clear with the way I'm communicating the messages, but it doesn't have to be like that. Just be very clear. So what do we do with plaintext? Well, we encipher or encrypt it. So encipher or encrypt. So what does this mean in plain language? To make plaintext ideally, so I'm just going to put ideally in there, just to ideally unintelligible intelligible except to its intended recipients or recipient. So I have this plain text. I want to send it over this communication channel. What I could do is I could encrypt the plain text, and what I get as a result is what we refer to as ciphertext. So this is just simply the message. The message after the encryption or encryption. So I'll write this in uppercase letters, but just to be very clear, often when I talk about how I encrypt, I need a cipher or cryptosystem. That's what we use to encrypt. So I'll refer to this as a cipher or cryptosystem, which will define what a cryptosystem is in a moment. So this is a particular method of encryption. And I must stress that depending on how technically you're going to get with what we refer to as a cipher or a cryptosystem, typically this might refer to the encryption or decryption algorithms. So the decryption naturally takes the encrypted text, the ciphertext, and brings you back to plain text. We'll talk about that in a moment, but often cryptosystem may also entail what the keys and how they get distributed also might be as well. For us, this will be relatively simple in today's lecture, but there can be more details to the cryptosystem. A particular method of encryption. So suppose if I were to give it a name, say I could call it capital EK, where K is its key. Where K is the key. So why exactly and how do we exactly consider if something is secure or not? Well, one way we can go about trying to do something like that, we're going to go through cryptanalysis. So one way you can go about assessing the security of a crypto system is through cryptanalysis. So what is this? So what's the game when you're dealing with cryptanalysis like this? So this is the process where the receiver of the ciphertext which, what would it be? It would be the result of applying the cryptosystem with key K to message M. So this is the process where the receiver of the ciphertext determines M. So I'm just going to abbreviate determines with deter with a, it determines M without prior knowledge of K. So without knowing the key. So often the goal here is to try to find out what the plaintext is, but more importantly, the key. So if somebody is using this key to encrypt messages in the plaintext, if you can get the hold of that key, presuming that this person is using this specific key all the time or frequently, this could create a vulnerability in such a crypto system, making it not as secure. It has poor security, potentially. So this is one way you might go about doing this, is by performing cryptanalysis. So let's put this all together. I'm going to be needing to define a little bit more carefully what a cryptosystem is, or cipher. Now, before I do this, I just want to illustrate these main concepts here, and then we're going to see how they formalize. And then we'll see how that all comes together when we start talking about what a communication channel is. I need help from Miss Kitty, though. So what I want to imagine is, imagine I have this box, and this is where I want to put my message. And imagine there's a communication channel here, some way to take and transmit the message from here. My message is going to go right here. I would like to put it in that box. So one way I could try to protect it from vulnerabilities, as in someone stooping in on the messages to find out what they're saying, is I can use a cipher to encrypt the message. So imagine I wanted to take my message. My message is in fact Miss Kitty. I'm going to take Miss Kitty and put her in the box, because you know kitties love going in boxes. So imagine my message M is Miss Kitty. So I have Miss Kitty is my message. So Miss Kitty's going to go in the box. I'm going to encrypt Miss Kitty. And then I'm going to take Miss Kitty, the message, I'm going to transmit it to the desired destination, for which I can decrypt it, and I get back my message. And then I have Miss Kitty in the box, and she's awfully happy over there. So the idea is that I give you plain text, so I want to use my cipher to encrypt that, or encipher it. I get ciphertext. The box here, when I transmit it, when she's inside it, that's my ciphertext. And I send that over to where it needs to go, across the channel, for which it can be decrypted. So that's the process of taking ciphertext and returning it back to being plain text, using the known key that both parties agree on. Again, I'll go into more detail about this. And of course, if ever someone wanted to find out that I sent Miss Kitty, they might go through a process of cryptanalysis. So specifically, they would want to know how I put Miss Kitty in this box, and how, and specifically what key I use. So for example, if I were to put a lock on the box, I wouldn't do that because Miss Kitty's in here, right? But I don't know, she isn't calling for it today. But suppose that I did have a key for it, then that'd also be a rather important piece of information, depending on what cipher we're talking about. So I'm going to be adopting a definition that's fairly common for what a crypto system is. And I must stress that when somebody refers to a cipher, very often they're referring to the algorithms, rules, or methods for which you use to convert for encryption and decryption. The process of me putting Miss Kitty in the box and taking her out of the box. So let's define what a cryptosystem is. So a cryptosystem is a quintuple, so that's a 5-tuple. It's going to have fancy P, fancy C, fancy K. That's supposed to be fancy. A fancy E, and a fancy D. Where, let's define each one of these aspects. So fancy P is a finite set, consisting of possible plaintext. Possible plaintext. Naturally, C would be a finite set as well, right? A finite set of possible ciphertext. Now, fancy K, this is going to be what we're going to refer to as the key space. Fancy K is called the key space. The key space. A finite set of possible keys. So these are all the possible keys that can be used for encryption and decryption. Finite set of possible keys. And now I got to talk about those last two over there. So we're going to have to be a bit careful about this. I'm going to need it so that there exists keys over this key space, and I'm going to define encryption and decryption in relation to each one of these keys. So for every key K in the key space, where there is an encryption. So I'll refer to it as an encryption, but it's an encryption rule, encryption function. So this guy right here is going to consist of a whole bunch of encryption rules depending on key K. Encryption with a corresponding decryption, DK. I'm not thinking Donkey Kong here. It's literally D subscript K. So that it has the following properties. So that, let's define what each one of the EKs and DKs would be and the property they would have. First, each EK is a function that maps, it takes plain text and it gives me a ciphertext. Each DK, naturally, think back to thinking about the box. When I put Miss Kitty in the box, she's encrypted, right? So I need to decrypt it. But that means that the box with Miss Kitty in it is ciphertext, right? I've obscured it. You didn't know that there was a cat in there, right? You didn't know that there was a cat. So, except that you've probably seen me put the cat in there. So it takes ciphertext and it outputs plain text. And the third and most important property here is that if I apply the decryption with key K on the encryption on my plaintext, or say this could even be a symbol in the plaintext, that distinguishing remark that I'll make, I'll talk more about that when we start talking about the communication channel. But it has to be that if I give you the encrypted the encrypted text, the ciphertext, when I apply the decryption, it gives me back the plaintext X. For every plaintext X in fancy P, set of plaintext. So just a couple quick remarks, just to emphasize the things I was going to say before I define the communication channel, is it'll be typical for us to talk about the plaintext as a sequence of symbols. These could be, you could also treat these like numbers as well. In some contexts, it will be indistinguishable between the two concepts. So I'll try to be careful when I do things like this, because there's natural correspondences that exist between characters and numbers. So very often, it'll be typical that we'll run into cases where the plaintext is actually of the form of a sequence of symbols, as I've defined it akin to up here. So you might notice that my definition, depending on how I define what P and C are, it might be the case that it might actually apply symbol by symbol. So in some cases, it'll be helpful for us to talk about the encryption and decryption by a symbol that represents plaintext, or you think of it as a sequence of symbols, and that is the plaintext. But often we'll talk about it in different contexts like this. So if I imagine I give you the plaintext X, it could be that the case is that it's really just a sequence of symbols. So I might treat this one and the same as X in this definition, or I might use just one symbol. So some xi could be X in this definition here. And when I talk about the plaintext here, I might be referring to what the symbols can be versus what they can be encrypted into. So please note that when I talk about this, it could be the case that it could be or to xi. And naturally, when you think about each one of the symbols, it is that I apply the encryption and I end up with a ciphertext, which is going to be a symbol of the ciphertext. That when I naturally apply this, I get back the symbol that would have been in the original plaintext, or the message. So it's just a technical remark that has largely to do with how I define what the crypto system is. In our case, we'll think about it symbol by symbol. We'll apply the encryption rule or encryption to each symbol. So let's talk about the communication channel now. We'll see how we can talk about what we just did over here with Miss Kitty. And Miss Kitty's still in the box. So here's how we could think about this. So messages. So I'll lovingly refer to this as the Alice Bob or Bob Alice model for cryptography. That's what I usually refer to it as. But and usually people will know what you're talking about. But I must stress that you could specialize this model or take and change little aspects of it. So messages are sent over a communication channel. So I haven't really told you what that means yet. Communication channel. And this is involving two agents. Channel from agent A. So I'll refer to this as Alice, to agent B, and this will be Bob. So so you want some examples of communication channels where the channel itself can take many forms. And it has, historically speaking, right? You'll see when we get to more examples that these things, this is a model. So the channel itself could mean many different things. The point is that if it fits the model, then most certainly it applies. It can take many forms, such as a phone line. So a phone line you can think of just this scenario, right? Alice is talking to Bob about her favorite supper dish, for example. It could be the case that is what is happening, such as a phone line. Such as a phone line, a radio wave. Could be a radio wave, as would be the case in some scenarios, such as a military, historically speaking. It could also be it could be a computer network line. Be something you'd very often run into, such as with some websites where you have secure information across them, or so-called secure information. It could be sent over a network. So Alice wants to send a message, send plain text, just to put it in our terms, send plain text to Bob. So this plain text could be many different things. It could be English text, for example. It could be numeric data. But here's what Alice is going to do. So I'm going to draw a picture. It's going to walk us through step by step, akin to something we just did over here. So I'm going to draw some fun pictures. So suppose we have Alice here. Give Alice a pretty dress. So here's Alice. This is A. And suppose I have Bob over here. Now let's have Bob. Here's Bob. Now, the thing that I would like to have happen is, imagine Alice wants to send Bob a message. So we're going to modify this ever so slightly as we go along, just to think about this. So suppose Alice sends message X, the plain text. Alice would like to make sure Bob gets this text, right? Gets X. So Alice will send it, so sends X, and Bob receives. Receives X, right? But we have to be careful, right? Because as we talked about before, this communication channel, if I want to ensure there is security, that X gets to Bob without anybody else knowing what X is. That's at least one aspect of this. So let's put this into this model just to make sure it's a little clear what we got going on here. So I'm going to introduce a third actor and third agent, a very keen one. I give this character a beautiful set of glasses. Some beautiful glasses. I'm going to refer to this actor as, or agent, as Eve, or Agent E. So suppose that you do send over this channel, you send message X. So you send the plain text X. In the current setup, what would happen? Well, most certainly if Eve is eavesdropping, then most certainly Eve can get your communication, right? Your message. So for example, if you're talking about your favorite supper dish, say you made a really great pizza the other day or something like that, who knows? Eve is going to find out all about your lovely supper dish. So we need to do something a little bit here if we want to improve the communication channel. Namely, we want to make it more secure, right? Ensure that Alice and Bob's message can't be intervened by Eve and be understood by Eve. So the and part is very important. Most certainly, if we're using an insecure channel to do this, there's reasons why we might do that. We want to make sure that the message is absolutely just garbage if we can. We would like to make that message garbage for Eve. So Eve just can't simply just know what you're making for supper, okay? So we're going to introduce a couple of things. So we're going to want to have it as we talked about. Maybe Alice will encrypt X. So we're going to have encryption. And imagine that this encrypted message, the ciphertext, becomes Y. Now, to take this and turn it back into X, we have to apply the property we had for our crypto system, right? We need the decryption algorithm. We need to decipher it. So we're going to have some decryption in place. That is going to, so we're going to encrypt. And we're going to need the decrypt. So notice that if I do a very good job of encrypting X, I get Y. I send Y across this channel, and I must stress that this is an insecure channel. I mean, somebody can listen in on this channel. So it's an insecure channel. Somebody could just sit there, they put a big earpiece on and just listen in on what's going on. That's the hypothetical, of course. What Eve might do is just simply want to listen, but Eve could take a more malicious role, where Eve actually has more capabilities than just this. So in cryptography, a big element of this communication is what techniques can you use to deal with adversaries. So for example, Eve is an adversary. So in this case, Eve's intention isn't necessarily malicious, but most certainly it plays a competitive role in the sense that we don't want Eve to know what X is. So we send Y instead and hope that Eve can't just simply figure out what the key would be and naturally the original message X. But there's something that we brought up when we talked about encryption and decryption. Well, we had this notion of a key space, so naturally we're going to need something to, we're going to have some source for those keys. So whether it be some pseudo-random number generator or something along those lines that both parties have agreed upon, or it could be that they both just wrote down the secret code that they would like to use as to make their keys. I don't know, but the point is that this is going to be broad enough that we have it where both parties have a key. Now, it might be more general than just this, just to be very clear. But the point is, you imagine that there is a key that is given over a secure channel. So as a quick example of what a secure channel would be, is me taking, suppose that Alice takes key K and physically gives it in an envelope over to Bob. Just as an example. There's other ways you can have a secure channel. The point is somebody can't just simply eavesdrop on this. But the point is we need this key for encryption and decryption as per our definition over there, right? So when Alice sends X, Alice encrypts X to get Y. Y gets sent over this insecure channel over to where Bob is at. Bob has access to the same key, or at least the key necessary to decrypt Y so that Bob receives X. So this is what the communication channel is. So this is the model for which much and many aspects of cryptography are studied over. So I must stress that, like I said, Eve is just one character. There's many other types of adversaries you could have. For example, Eve could take a far more malicious role or a far more controlled role in the sense that Eve could, for example, be not just listening, but could, for example, have the ability to mutate the message. We're not going to study that scenario here, but most certainly that is another aspect of the communication channel, which you can study in different ways. But we'll just think about Eve more as just this adversary that has a vested interest in our supper dishes, okay? They want to make their own cookbook out of our favorite recipes. So you might ask, Dan, if you're looking at this model, you might be staring at this and saying, Dan, why don't they just send X over the secure channel? Why can't they just do that? Well, one major issue with doing this is it's fairly expensive. Did I mention just that, like in my example? And I want to stress this doesn't have to be the only way to do it, but you just imagine every day you want to send a message over to Bob. Say you're sending an email, and you want to make sure that these are top secret emails that get encrypted or something. You wouldn't want to have it unless you absolutely just sat there and said, this is the only form of technology we got, where Alice physically hands Bob the message every single time. That might work for some applications, but it's fairly costly if you have many messages you would like to send, right? And here's the benefit. Well, all sorts of things, like you might know about this thing called the internet, for example, and it makes it so you can route messages over the internet. And if you would like to send messages over the internet, it's not necessarily going to be the case that it's going to be secure. It's going to be very often insecure. And that's much cheaper for sending messages. At least if we're thinking about if Alice and Bob were on the other side of a city. That could be a lot of money over time. So the other thing I also want to point out is that the secure channel could also be slower. So we can put this into all sorts of different settings. It could be, for example, that if we thought of Alice and Bob as, say, let's go back ancient times. Suppose that Alice rules one kingdom and Bob rules another kingdom. Well, Alice could physically hand Bob the message, but instead Alice might want to instead use a messenger, maybe a pigeon or something like that, I don't know. The point is, using a messenger, that is one layer of now transmitting that message, so putting it in an envelope and giving it to the messenger to bring it to Bob. Well, there's a lot of stuff that can happen in between here, right? So if I do it directly, remember, Alice, that's very expensive to bring Alice over to Bob to give it over, right? Or like even having the keys and bringing it over. It's something you don't have to do as often, so it's much more feasible. But if Alice just were to go to see Bob every single time, well, what happens to Alice's kingdom? Well, I don't know. That seems like an awfully expensive thing to do, right? But the point is, sending a messenger instead, it might leave you vulnerable to someone finding out that message, whether they steal the message from you, from the messenger, to be a bit more precise, or do something else with the message. The point is that you would like it so that it's cheaper for you to send messages, right? But there's a trade-off in this, is that you can leave yourself open for vulnerabilities. And one way to deal with insecurity is by introducing security. And one way to do that is making your messages unintelligible to someone that might want to know what you're talking about, whether it be your favorite recipe, or this could be military codes. So, just as a general principle, so assume that the knowledge of the general system or algorithm for encryption via EK, or say if we're talking about like one individual symbol or perhaps the entire message, say for example, if we consider just more broadly like this, for key K is known to Eve. Suppose Eve knows this. Suppose that Eve just doesn't know what the key is. That seems to be a pretty fairly reasonable assumption if we're talking about security. So only the key K is assumed not to be, I'll say not known. Not known to Eve. So remember, Eve can receive a copy of the ciphertext. So we're going to use the general principle. This is the one we're going to measure by. Is assume that this person, Eve, could know the general system and the encryption for how the encryption is done. But they know it for a particular key. possibly. But they don't know what the key K is. So that's going to be the vulnerability for which we would like to improve our security. So we'll be interested in techniques for which we carry out this process, such that we want to make sure that Eve can't figure out, or at least buy ourselves as much time as feasibly needed so that we could send the message over from Alice to Bob. So in many settings, it will just be a question of time when it comes to security as opposed to true security. But I'm getting ahead of myself. But what we're going to do is we're going to study various ciphers and cryptosystems in relation to this general principle and try to measure how good or bad, at least in some standard, akin to something of like this, these different cryptosystems can be over this type of scenario. In addition, we'll also study all sorts of other scenarios related to cryptography.